Do you have any questions before we start about the material that we had covered before? I mean, I will just make a summary of the things that we will be discussing this week. There's not much actually. But before starting that, if you have any questions about the material we had covered up to now. Okay, so let's review that again. So what we had done, we had this system, two medium. One had the electrical permeability epsilon 1, the other one had epsilon 2, and here we had a plus Q charge. And then we said that for an observer in region 1, there is a single image charge that we called Q double prime. So in region 1, the potential was basically 1 over 4 pi epsilon 1 Q double prime divided by R minus R1, R minus R double prime, R0. Yeah. 1 over epsilon 1. Okay, this was the potential. Well, we already know what the field lines corresponding to this one look like. So these are just radial lines from the position R0, right? So in region 1, the electric field lines are just straight lines. They are converging to the point R0. And Q double prime was twice epsilon 1 over epsilon 1 plus epsilon 2. So we know how the field lines should look like. So whatever epsilon 1 or epsilon 2 are, as long as epsilon 1 is non-zero, they will be straight lines. This is in region 1. Now, in region 2, we said that there are basically two charges, one the actual charge, and then there is its image, Q prime, and this Q prime was equal to epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1. So basically it acts, and in region 2, we have somewhat a dipole. Dipole in the sense that we have 2 point charges. And the electric field will be the electric field of 2 point charges. And this second charge, it depends on which medium has the larger dielectric constant. So let's see, if epsilon 2 is larger than epsilon 1, then Q prime is positive. So we have a positive charge here, and we have a Q positive charge here. This is our the region separating the two. And well, of course, it will depend on whether how big Q prime is, but it will have more or less the electric field lines will have such a shape. Of course, in this region, we don't actually have electric field lines. We are interested on region 2. So this is how the electric field lines in region 2 will look like. Now, if epsilon 2 is less than epsilon 1, then Q prime is negative. So we have Q prime less than 0. We have plus Q over here. This is the surface separating the two. So these two field lines, the electric field lines will look something like this. In region 1. I'm sorry, in region 2. And then I just combine the two. So let's say for the case epsilon 2 is larger than epsilon 1, the electric field lines in region 2 should bend towards the surface, and then in region 1 they should just continue perpendicular as a straight line. So the electric field lines will look like this one. These are how the electric field line looks like. Remember, these are the E lines. And you see that at the boundary, at the interface, the electric line is not continuous. Well, we already know that the electric field line will be discontinuous because we know that the curl of the electric field line is always zero, electric field. This tells us that at any interface, the parallel component of the electric field line is always continuous. This is always true. But the perpendicular component of the electric field line is not continuous. Let me write it as rho plus rho b. So this tells me that the change in the component of the electric field line perpendicular to an interface is always equal to 4 pi sigma plus sigma b. Now, in this case, we have a dielectrics. We only put a single charge at the point R0. So the sigma is 0. But since the medium is polarized, sigma b is non-zero. So let's see, E1 will be equal to 4 pi sigma b. Now let's see whether the surface charge is positive or negative, in which case. Now let's see if epsilon 2 is larger than epsilon 1. So that tells us that the second region is more polarizable. There will be more dipoles in region 2 than in region 1. In the interface, we have, let's say, these two neighboring dipoles. The dipole in region 1 will have a larger magnitude than the dipole in region 2. No, region 2 will have a larger magnitude than the dipole in region 1. So the negative charge of this dipole will be larger than the positive charge of the other dipole in region 1. So the surface charge will be negative. Well, that is in fact why we have this negative image charge. Well, the surface charge is negative. The sigma b is negative. If sigma b is negative, it just means that the perpendicular component gets smaller as you cross the boundary. Now that is actually what we observe. Perpendicular component becoming smaller basically means that the electric field line, electric field vector approaches the surface. And this is what we observe. Any other questions? Yeah, actually they do. Yeah. Yeah, a p-n junction is basically the interface of two different dielectrics. Semiconductors in that case. Well, with the method of images, we had solved two problems: one, the charge in front of an infinite conductor and the charge in front of a sphere. Well, this week we basically study the same example. So we have a region. In this region, we have a spherical second region. And they have different dielectric constants. And we put a charge nearby, for example. Again, you can solve it with the method of images. The idea is basically the same. But of course, the thing you have to be careful about is when we were discussing the method of images for a conducting sphere, inside the conductor there was no electric field, so we didn't need to worry about it. But in this case, inside the conductor there will be an electric field, and hence for that electric field there is it won't see this plus Q, but mainly it will see a different charge. That's the main difference. Then there is the problem. There is a question. So, okay, so we have these examples. We know that the displacement field is defined as the electric field, the external electric field, plus the 4 pi times the polarization. And this polarization essentially gives us some kind of a bound charge density, and the normal component of the polarization, normal to the surface, behaves like a surface charge density. In fact, it is a surface charge density. And for linear materials, we said that the displacement field will be proportional to the electric field, and the polarization will be proportional to the electric field also, and the relation between the two is just the dielectric constant, or the electrical permittivity, is equal to 1 plus 4 pi times the electrical susceptibility of the material. Well, these are all defined in terms of the macroscopic properties, but every material is basically made up of atoms, and this polarization is caused by the polarization of the atoms. And this chapter, the remaining part of this chapter, is mainly about how we can relate this electrical permittivity and susceptibility of the material as a whole to the polarizability of the atom or the molecule, whichever one we have. So how can we relate the two? Now, the problem with that is, you see, when we are defining this electric field, what we will be calling the electric field will be mainly the average electric field. And this is average over a volume that is small compared to the macroscopic size, but large compared to the atomic or molecular distances. So that is how we define this electric field. But if you think of in terms of the atom, now the atom doesn't see this average. The atom sees a local electric field, which can be highly fluctuating. And this local electric field will be different than this average electric field. And hence, what causes the polarization of the atom will be the local electric field, not this average electric field. So we have to first study how these two are related, how the local electric field and the average electric field are related. Now, what we say is the local electric field, well, there is the average value plus, let me write these first. Now, what these mean is that we have this material. We are considering the local electric field at the position of this atom. We separate the system into two. Again, if you remember when we were talking about the averages, we had basically did a similar thing, because for molecules that are large away, we have a different treatment. For molecules that are close by, we should have a different treatment. And the same idea applies here. So this is equal to we first remove away that part, except in the atom, and we remove the rest. So here we have a material. Inside there is a cavity. Inside there is a cavity. It is polarized due to the applied electric field. So since it's polarized, let's just, for simplicity, let's assume that this is the direction of the polarization vector. On the surface, there will be charges. So this side will be slightly negatively charged, this side will be slightly positively charged. So there will be the electric field created by this polarization. This is what we call EP. And then there is the atoms inside our volume, all the other atoms. They also create some kind of an electric field. And this is what we call EI. Plus, of course, there's the external electric field that we apply. So there's this E. External or average. So these are the sources of the electric field, sources of the local electric field. Now, the polarization, in fact, doesn't need to be uniform, but the volume that we are considering is very small. For such a small volume, we can assume the polarization will be almost constant in that volume. So if we have a constant polarization, the corresponding electric field created by the charges of this polarization will also be the same. It will be uniform. The problem is mainly with this internal electric field created by the charges nearby. So for that, you need to have a model. And for the treatment, I mean, you cannot really make a general treatment. It depends on the material, it depends on the material properties. But in the book, for example, it has the simple cubic lattice. And for the simple cubic lattice, it assumes that, okay, there is one misconception, mainly caused by my stress on the fact that the dipole expansion is a long distance expansion. You see, this expression QL over R to the L, QLM, YLM, omega. If you remember, this is our multipole expansion, and we had defined this QLM as the integral of the charge density multiplied with R to the L, YLM star omega. Now, this expression, summed over all possible values of L and M, is valid, whatever the value of R is. The only restriction we have on that summation is that the R should be, this expansion of the potential is valid outside the charge distribution. So if you have a localized charge distribution, if you are outside that charge distribution, that expression of the potential is always valid. It doesn't have to be very far away. So if you have this charge distribution over here, for this point right at the edge of this charge distribution, that potential expression is still valid. There is no problem with that. Now the problem arises if, that sum contains infinitely many terms. The problem arises if you try to cut that expansion. In the sense that if you just say V of R is equal to Q0 over, this is L plus 1 over R plus Q1 M Y1 M divided by R squared and from -1 to 1. If you say that this is approximately true, then there are two possibilities. For some reason, the other neglected terms have to be small. So you have to argue that. One possibility is that if small r is much larger than the size of your charge distribution. One possibility is, let's say, d over r is much less than 1. So you have this, your charge distribution, whatever the charge distribution is. So it has a typical size. Let's call it d. If you are at a distance much larger than this d, then the other terms are negligible. This is one way. Or, so this tells us that at faraway distances, the dipole approximation is good enough. But if QLM is approximately 0 for L larger than 1, for some reason, it might be that the atom only has a dipole, this quadrupole, hexapole, etc., multiple moments. They might vanish, or they might be negligible. In that case also, this approximation is correct, even if you are not far away from the charge distribution. So that is an approximation. That is the thing that the book uses. It says that, okay, to model this EI, let's assume a cubic lattice of atoms or molecules that only have a dipole. So these atoms or molecules are not very far away from my point. So the dipole approximation is not exactly justified because we are not at a faraway point, but it is still justified. It's not justified based on arguments of distance, but it is still justified because the molecules only have a dipole moment, higher moments vanish. That is the assumption. And in that case, also assuming that the dipole moments are all aligned, the book says that, okay, this EI is 0. Of course, not for glass, for example, we cannot really make the cubic crystal approximation, or the dipole moments of each one of these atoms or molecules might not be aligned, etc. There are all reasons why this approximation might break down. But nevertheless, for most materials, it will be a good enough approximation. And of course, if you are doing actual research on an actual material, particular material, you have to devise a model based on that material. But for general grounds, to get some kind of a deeper understanding of what is this polarization, how it is related with the microscopic properties, etc., this simple model is a good enough model. And in this model, things are quite simple in the sense that EI is 0. So each one of these dipoles in our volume, they create a net electric field that is 0 at the origin. In fact, if you remember, we had also made a similar analysis of the electric field created by these charges only in our volume. If you remember, we had discussed the average electric field. Well, we didn't really discuss the actual electric field, but the average electric field was proportional to the polarization. Now let me just skip that. And it turns out that in this case, in the simple model, the electric field at the center at least is 0. And in this way, we know the local electric field, EI is 0. We know this uniform electric field created by the polarization P. We know the external electric field, and the dipole moment of the molecule will be nothing but gamma molecule times E local. And you can relate the epsilon and chi, the electric permittivity and the susceptibility, to gamma mole. So the polarizability of the molecule. Okay, this is kind of the first step, how to relate the macroscopic properties to the microscopic properties. Then the second thing is, what about these microscopic properties? How can we study this gamma molecule? What does it depend on? There are basically two important mechanisms to polarize an atom. One is that if you have an atom or molecule that is not polarized, so you can, the simplest model you can think of an atom or a molecule, or an electron in the atom or a molecule is you have the nuclei, and the electron is kind of attached to it by a spring. This is the simplest that you can think of. Of course, this is not a very realistic picture, but it's good enough. And what will happen is if you exert an external electric field, the spring will have a different equilibrium distance, which will be shifted from the previous one by a constant. A constant multiplied by the electric field. And since the electron is shifted, that creates a polarization. And considering that, okay, classically speaking, the electron will have, let's say, a circular orbit. And for very small deviations around the circular orbit, you can always make this harmonic approximation. So very close to that orbit, the electron will behave as if it is attached with a spring. You see, effectively, the effective potential that the electron will feel. You will see this in classical physics, if you haven't seen already. Have you studied the central problem in classical physics? The effective potential will have such a form, more or less. Here, at the bottom of the well, it is nothing but a parabola. So the potential at the bottom of the well is a parabola, which is nothing but the potential of the spring. So these two problems, as long as you don't cause a very strong deviation, they will behave identically. So this is one origin of the polarization. Another one is the rotation, if the molecule has a permanent dipole. For example, one such molecule, you see, if you consider some typical molecules, carbon dioxide. Now, carbon dioxide has this shape. You have the oxygen at the center, carbon at the center, oxygen at two sides. There are double bonds. Now, these bonds each one of these bonds have a dipole moment. So since they are pointing in opposite direction, this molecule has zero polarization on its own. So if you don't apply an electric field, it has a zero dipole moment. But if you consider like molecules like H2, the water molecule has this shape. You have the oxygen and then the hydrogen bonds. They are at such an angle. Again, each one of these bonds are polarized. They have a dipole moment. So if you sum them up, the total is non-zero. Now, in the first one, of course, you apply an external field. It will polarize, creating a polarization. In the second one, the dipole moment is already there, but in general, it will be randomly oriented. So one molecule will have a dipole moment, let's say, up. The other one will have a dipole moment down. The other one in this direction. The other one in the opposite direction. On the average, you get zero polarization if there are no external electric fields. Now, if there is an external electric field, the external electric field will try to align them. But remember, these molecules are constantly moving. Even in solids, they are vibrating and colliding with each other, basically. In gases and liquids, they will be wandering around, like in water, they will be wandering around and again colliding with each other. And at the end of the collisions, there is no guarantee that this dipole moment should have exactly the same orientation. So the electric field tries to align them in the direction of the electric field. At the same time, collisions, they just scatter the direction. So there are these two influences. One is the collisions, which will in general randomize the direction of this dipole moment. Plus there is the electric field, which will try to convert to rotate them in a given direction. So whichever one, the total dipole moment depends on whichever one wins, or how much each one is successful. Now the collisions are due to the motion of this molecule, which is what we call the temperature. Remember, temperature is the average kinetic energy of the molecules. You can identify the two. So if you increase the temperature, that means there will be more collisions in a given amount of time. So it's these vibrations will randomize the system more. If you lower the temperature, well, there won't be many collisions, so the electric field will rotate them. Now, you haven't seen electrostatics yet. I'm sorry, not electrostatics, but statistical mechanics. You will study electrostatics next year. But the basic idea is that you will see that we have many molecules over here. So if there is no external electric field, the probability of the dipole moment having one orientation or the other orientation, they will all be equal if there is no electric field. When there is an electric field, there will be a slight more prejudice for the dipole moments to be aligned in the direction of the electric field. And the probability for having some dipole moment will be, let's say, proportional to h power minus v over kT. Kb, the Boltzmann constant, T is the temperature. So if T is equal to 0, the most probable state will be the one that minimizes the potential. And V, for a dipole in an external electric field, will be minus P dot E. So as T goes to 0, then the smallest possible value of V will make the largest, will have the highest probability. And for the smallest value of V, P, and E should be in the same direction. So in 0 temperature, mainly they will be aligned with the electric field. At very high temperatures, when let's say T goes to infinity, well, the exponent, that factor basically becomes 1 independent of P, and hence all polarizations are equally probable. And at intermediate stage, this is the expression for the probability to have a given dipole moment for an individual molecule, from which you can calculate the average molecular polarizability, which you can relate. This will be equal to gamma mole times E, and from this gamma, you can calculate the gamma mole using this probability amplitude. That is basically what the book does. What is the dimension of gamma? Let's see, what is the dimension of the dipole moment? Q dot D, which is stat coulomb meter. Or let's write it in this form. The charge of unit of Q times the unit of D. Now, what is the unit of electric field? Unit of Q divided by unit of D squared. Now, let's see, the unit of gamma mole is equal to the unit of P divided by unit of E, which is QD divided by Q over D squared. Well, Q's cancel. This is the distance Q, or volume. Well, typically gamma will be the volume of your molecule. So you see, since it is a volume, and it cannot be smaller than 1, it cannot be larger than 1. It cannot be compared to 1.
About 1 meter cube? 1 meter
Well, you see, gamma mole will be typically V0. So you can compare that now to 1 meter cube. Now, another thing to pay attention to, especially in this orientational polarization, is that you see, if the molecule has a dipole moment, it will still be polarized additionally due to the applied electric field. So you have this water molecule, which has a permanent dipole moment, which is randomly oriented. If you apply an external electric field, it will, one, orient this dipole moment, two, change this dipole moment, because it will cause the additional shifts in the charge distribution. But normally, these additional shifts will be negligible. So even when you put this, the water molecule in an electric field, it will still have exactly the same dipole moment, just in a given direction. So when you are talking about the probability over here, it is basically the probability of the orientation of the dipole moment. The magnitude doesn't change. So that's why when you are calculating the average dipole moment, you have to average over the directions.
Calculating the average cosine alpha, why do we take integral over d omega?
Well, you see, you didn't yet study statistical physics, but the basic concept of statistical physics is that, I mean, the quantities do not have fixed values. So every value is probable. So every orientation of the dipole moment is probable. Now the question is, what is the probability for it to have a given direction? And that probability is usually given by this Boltzmann fact, what we call the Boltzmann factor. So for a given system, the probability that it will have an energy E is always proportional to the exponent of minus E over kT. Now in this case, there is only the potential energy, so that's why I wrote minus V over kT. That is the probability that the system will have a dipole moment P, where this potential energy is nothing but minus the scalar product of P and the applied electric field. That is the potential in an electric field. Now, the magnitude doesn't change. Well, it changes very slightly, but we just ignore it. It's just the orientation that changes. So my system can be in a state that is described by the orientation of this dipole moment. Now, the dipole moment can orient in any direction. So if we are talking about the average, we have to average over all these possible orientations with that probability weight. So that's why we are integrating over the solid angle. So integral over the solid angle is just an integral over all possible directions. We have the probability of a given direction. We just multiply and calculate the average. You multiply the probability with the dipole moment, and integrate over all possible outcomes. It's just like the average in quantum physics. The wave function squared gives you the probability distribution. You multiply it with a possible outcome. You multiply a possible outcome with its probability and integrate over all possible outcomes. Here, instead of the wave function squared, we have this Boltzmann factor. Of course, you have to properly normalize it to 1. Now, time for your questions. Well, let's discuss an example. I mean, you will tell me what to do. Okay, in the book, one of the examples that is studied is you have a medium. Let's say with electrical permittivity epsilon 1. Inside there is a spherical region, let's say the electrical permittivity epsilon 2. And you put this, and there is a uniform electric field far away from this sphere. Let's call it E0. So what is the electric field everywhere? And well, there is a solution in the book, and in the book it just says, oh, the system will be uniformly polarized, both the sphere and the outside, so we use the results for a uniform polarization, there is all the dipole moment, etc., etc. But let's say you didn't see that. What else can we do?
You can separate the system.
Hmm?
We can separate the system.
Now, first of all, what are the equations that we have that we need to solve? You see, we have the divergence of the displacement field and the curl of the electric field. For this system, what is the divergence of the displacement field? Hmm? What is rho? What is rho b? Hmm? Well, you see, how did we define the displacement field? Four pi p, right? Now, the divergence of the displacement field is the divergence of the electric field plus 4 pi times the divergence of the polarization. What is the divergence of the polarization?
Just charge.
With charge. Hmm? You see, the divergence of P doesn't refer to any surface, so it cannot be the surface charge, but it can be the bulk charge, minus rho B. What is the divergence of the electric field? Giray? 4 pi? No. Rho plus rho B. You see, now what we call rho and what we call rho B are different things. The total charge density is rho plus rho B. But rho is the charge that we put in the system. Rho B is the charge created by the displacement of the charges already existing in the system. So if we just plus 4 pi times minus rho B, they just cancel. Or in a sense, this rho, we can also call it rho free. Sometimes in some books it will be called rho free to avoid any confusion. So the divergence of the displacement field is 4 pi rho free. Free meaning that it's us that put it over there. Rho B is the charge created due to this displacement of the displacement created by creating the polarization. I mean, when you put your system in an electric field, it's basically shifted the charges. And when the charges are shifted, it creates a charge distribution in our system. But that's not something that we control. So we just kind of separated the charges that we control plus the charges that we cannot control. The charges we cannot control, we just parameterize their effects in terms of the polarization. So back to our system, what is the divergence of the displacement field in this system? This is the general expression of the divergence of the displacement. What is rho free in this case? No. I mean, free meaning that the charges that we put, I mean, even if you have insulators, if you put a charge over there, that contributes to rho free. No charge is put, zero. Divergence of P is always zero. Not always, in the system it is zero. We didn't put any charges. We just put our system in an electric field, which was probably created by some charges at infinity. We don't care about those. In our volume, divergence of T is zero. What is the curl of the electric field? It is always zero. Whether you are in medium or not, the curl of the electric field is always zero, which tells us that the electric field can always be written as the gradient of some potential. This is always true. But whether you are in medium or not, the electric field can always be written in terms of the gradient in electrostatics. Now we somehow want to put this expression, put this relation between the electric field and potential into the first equation, so that we will get an equation for the potential. How can we relate the two? We have to relate somehow the displacement field and the electric field. But what about T? What about T? So, I mean, what we are interested in is displacement field. You see, there are two equations we need to solve for these two quantities, E and D. The second equation is trivially solved by just writing the electric field as the gradient of some function. But the first equation is also related to, although it is written in terms of D, it is also related with E. So what is the relation between the displacement field D and the electric field E? How did we define the permittivity? What was the definition of permittivity? But how did we define this susceptibility? I remember what we did was basically the displacement field was a function of the electric field in general. And we just assumed the Taylor expansion. A Taylor expansion will contain the linear terms in electric field, the quadratic, the cubic, the fourth order, etc., all those terms. But if the electric field is not uniform, the linear term would be enough. And we said that, okay, the displacement field, at least if we have an isotropic homogeneous medium, will be proportional to the electric field, and that proportionality constant is what we call the permittivity of the material. So this is the relation between epsilon and E. So we have this relation now. The gradient of permittivity times the electric field should be equal to 0. Can I take epsilon out? Is epsilon constant in our problem? Yes. Is it constant? Why not?
So the difference from the outside of the sphere and the
Inside the sphere. So epsilon is not a constant. So it has two different values. But then we can get rid of this problem by just saying that epsilon, by just trying to look for a solution in two regions, as you had proposed. This is region 1, this is region 2. Is epsilon constant in region 1? Is it constant in region 2? Yes. So both in region 1, inside region 1 and 2, epsilon is just constant, either epsilon 1 or epsilon 2. So I can take the epsilon out. Epsilon times the divergence of the electric field will be 0. Divergence of the electric field in both of these regions should be 0 because epsilon is non-zero. This tells me that the Laplacian of this potential should be 0 in both regions. So we basically need to solve the Laplacian. Which coordinates would you propose that we should use? So let's try to solve the Laplacian explicitly by using separation of variables. So which coordinate would you suggest to use?
Can we do one Cartesian coordinates?
Cylindrical coordinates, Cartesian coordinates, cylindrical. So why do you choose the cylindrical, Cartesian, or spherical? You like it more, or do you have a justified reason? Why do you choose one or the other one? At the end of the day, the solution shouldn't depend on which coordinate system you use.
Why in region 1? It's sine of the rectangular field, so the Cartesian.
What is the boundary of region 1?
Actually, there's no one. Is there any boundary?
No, you see, these edges, they go to infinity. So it's not just a finite volume, it's an infinite volume.
Okay, then there is no reason to choose Cartesian coordinates.
What's the boundary of region 1?
Boundaries are zero.
Hmm?
Boundaries are zero.
Boundaries?
Are zero.
What's the, first of all, what is the boundary? Then the next question would be, if there will be such a question, I will ask the value of the potential at the boundary, but first question, what is the boundary? Hmm? No boundary. What about the sphere? Isn't it a boundary of region 1? Hmm? You see, what do you mean by the boundary of a volume? It's the surface that limits your volume, right? So, in region 1, there are two surfaces that limit my volume. One is at infinity, but my volume cannot go inside this sphere. So that is another boundary, another limit of my volume. So region 1 does have a boundary that is not at infinity, it is my sphere. What about region 2? I mean, you see, the boundary need not be the outside. It is just a surface beyond which your volume doesn't go. So your points in your volume cannot pass. So that is another way that you can define your boundary. Your points in region 2 cannot pass through the sphere. On region 1, sorry, cannot pass through the sphere, so that's the boundary. For region 2, what's the boundary? Region 1 is not a boundary, it's a volume. Boundary should be a surface. Surface of the sphere is my boundary. So in both cases, both in region 1 and region 2, one of the boundaries that I have is this sphere. Now, which coordinate axis would you propose now? Cartesian. Why Cartesian or why spherical? Hmm?
Use spherical symmetry to explain the boundary. Just R equals some constant in our boundary.
So that is. So what do you say? Why Cartesian? He has an argument for spherical coordinates, saying that the problem has spherical symmetry.
I agree with the given one. First, saying it is good for choosing Cartesian. By the way, in region 2, is it spherical or just surface?
It's a sphere. I mean, you see, we have this volume that goes to infinity, filled with a material with the electric constant or permittivity epsilon 1. Inside this medium, we put a sphere with some other permittivity. Just imagine you are inside ocean, you have your ball, you put your ball over there and apply a uniform electric field. You also choose spherical. But you see, Cartesian should be fine if you want to suffer a bit in doing all those kind of computations, because the computational it will be quite challenging. But for spherical, it will be quite easy. Now, the easiest would be the spherical coordinates, mainly as Giray pointed out. The surface, the boundary, are easy to express in spherical coordinates. We have two boundaries. If we just choose our origin to be at the center of this sphere, and let's say this is the radius, so the two boundaries we have is R is equal to capital R. This is the boundary separating region 1 and region 2, and the other boundary is at infinity. That's since our medium extends up to infinity. So this is the equation we have. which we have to solve in both of these regions. Now let's start with the solution. Do you remember the general solution of Laplacian in spherical coordinates? So if you have the solution of a Laplacian, it can always be written in this form, in spherical coordinates. Are you familiar? I mean, we did discuss this, right? I mean, at least when we were discussing the addition of spherical harmonics, I remember that we had discussed this. So this is the general potential. Then we have the in region 1, this is sum over L and M, A, L, M, let's say region 1, R to the L plus B, L, M. In region 1, 1 over R to the L plus 1, times Y, L, M, omega. This is the potential in region 1. But you see, in region 1, we have this point R is equal to 0. But the potential should be finite, right? So what can you say about these constants A and B from this condition? B should be 0, because B is proportional to the inverse powers of R, and when you said R is equal to 0, they just diverge. If B is non-zero, you cannot have a finite potential at R is equal to 0. So the potential in region, sorry, did I write it wrong? This is region 2, not region 1. This is our region 2. Now let's look at region 1.
Maybe the potential is finite.
Yes, almost everywhere. Now we will see why I said almost everywhere. You see, if you have point charges, the potential need not be finite there. The potential can diverge if you have point charges. But here we don't have any point charges. Phi satisfies the Laplacian, not the Poisson equation. So it has to be finite, with the possible exception that it can diverge at infinity. Let's see, phi in region 1, that is outside our sphere, this has to be equal to sum over A, L, Lm, A, Lm in region 1, R to the L plus A, L, B, Lm in region 1 divided by R to the power L plus 1. Now we have the problem of what happens when R, in region 2, R can go to infinity. What happens when R goes to infinity? It diverges. Is it allowed? For example, if you have the point charge, it doesn't diverge. Well, let's see. This is our system. I mean, it's not if or whatever. We know the system. What's the potential at infinity? We are given the electric field at infinity. So what is the corresponding potential? Now let us also choose some coordinate axis. Basically, I will need this one. Let me choose this one as Z. As r goes to infinity, the electric field should go to E0. Which is E0 in the Z direction. I just choose the direction of E0 to be my Z direction. So what is the corresponding potential? I know the electric field at infinity, so what kind of a potential creates that? Well, if you have zero potential, then the electric field should be zero, because the gradient of the potential is gradient of zero or constant, they are both zero. Remember, the electric field is gradient of my potential. The gradient at infinity should not be zero. Okay, it will be infinite, but how? You see, I need to be able to take the derivative. So if you tell me infinite, it doesn't really tell me much. You should give me some functional form, which might diverge at infinity. As long as its derivative gradient gives me the electric field, I should be fine with it. What is the function whose gradient is a constant in the Z direction? Z. If you take the gradient of Z, that is just 1 in the Z direction. In this case, so it should be phi should be minus E0 Z, because the electric field is minus the gradient of this one. So this will give me an electric field in the Z direction. Let me write it in this form. Minus E0, because we are using spherical coordinates, which will be minus E0 or P1 of cosine theta. P1 is my Legendre polynomial. Remember, P0 of x is equal to 1. P1 of x is equal to cos x. P2 of x is equal to, the definition is 1 over 2, 3x squared minus 1. So this is the limit of my potential. Now I will do one more trick. Let's go back to our problem. Now, if I rotate my system around the z-axis, does anything change? Nothing changes if I rotate my system around the z-axis. But if I change my system around the z-axis, all the points, the phi coordinates of different points change. So if I shift the phi coordinate in my potential, nothing should change. So my potential should be independent of phi, the phi coordinate. Nothing should depend on the phi coordinate. But remember, this YLM functions are proportional to the Legendre polynomials times e to power im phi. So you see, the potential depends on this phi coordinate if there are contributions to my potential from terms that has a non-zero m. So the only terms that should contribute to those sums should be the ones that have m equal to 0. These should all be 0 if m is different than 0, because otherwise the potential will have phi dependence. Well, if m is 0, these YLMs are nothing but the Legendre polynomials, ordinary Legendre polynomials. And with some proportionality constant, with some normalization, which I can absorb in the definitions of these ALMs and BLMs. So I will basically rewrite my potentials. Phi 1 of r will be equal to sum over L, AL r to the power L, plus BL over r to the power L plus 1, PL of cosine theta. And phi in the second region will be equal to sum over L CL r to the power L of PL of cosine theta. And there was one property of this Legendre polynomials that I will use from -1 to 1, the theta, sine theta, PL of cosine theta, PL prime of cosine theta will be equal to 2 over 2L plus 1, Kronecker delta LL prime. Or, if you remember, we had discussed the orthogonality of functions with respect to some inner product. And for polynomials, one possible definition of this inner product is just you multiply them, integrate from -1 to 1. Both are the same thing. Now I have a simpler form for my potentials. There's still one boundary condition I can impose on my potential in region 2. Remember phi 2, no, phi 1 in region 1. As r goes to infinity, you see this is phi 1. As r goes to infinity, the terms proportional to BL, they all go to 0. So what I'm left with is sum over L, AL, r to the power L, PL of cosine theta, which should be equal to, you see, the potential when r goes to infinity is minus E0 r P1. P1 of cosine theta. Because we know that at infinity the electric field is uniform. That is why it is minus E0 r P1 cosine theta. P1 cosine theta is just cosine theta. But the reason why I write it in this form is essentially PL Legendre polynomials, they are orthogonal to each other. So if you have such an equality, the coefficients of PL on both sides should be the same. So the coefficient of P1 on the left-hand side is A0 times R. On the right-hand side, what is the coefficient of P1? No, sorry, A1. I'm writing the coefficient of P1 on the left-hand side. On the right-hand side, minus E0R. Or A1 should be equal to minus E0 AL, L different than 1. What is the coefficient of PL on the left-hand side? Where? Over there?
Coefficients of PL on the left-hand side.
Okay, AL times R to the L. This is the coefficient of PL on the left-hand side. What about the coefficient of PL on the right-hand side? No. Remember, L is not 1. It is 0. There are no other PLs on the right-hand side. So this should be equal to 0. So basically, AL is equal to 0 if L is different than 1. So now we know the A coefficients. Remember, inside the sphere, we could determine the B coefficients from the requirement that the potential should be finite. On the outside, we can determine the A coefficients because those are the ones that diverge. Either, if the potential was 0 at infinity, we could have just said that it should be 0. But in general, in this problem, at infinity, we have an electric field. So the potential cannot be 0 at infinity or a constant at infinity. It has some functional dependence such that the gradient should be a uniform, should give us a uniform electric field. So that it's just A1 that will give us a uniform electric field at infinity. The other ones should be 0. Now let's combine these two. So we now have the potential in region 2. We didn't do anything with it. It is CL R to the L PL of cosine theta. And in region 1, outside our sphere, we have the A1 term only, minus E0 R cosine theta. Plus, of course, we have all the other B terms. Okay, so these are the potentials in region 1 and region 2, the things that we can obtain only by imposing the boundary condition at infinity and the finiteness at the origin. So we still need to match these two potentials over the sphere. Remember, we have two conditions. The curl of the electric field is equal to 0. Well, this condition basically tells us the parallel component of the electric field across any surface should be equal to 0, continuous. There is no jump. Furthermore, the divergence of the displacement field in this problem is 0. We first determined that the divergence should be 0. And this tells me that the jump of the perpendicular component of the displacement field across a boundary is 0. So the parallel component of the electric field and the perpendicular component of the displacement field should be continuous across any boundary. Now, if the divergence of D was not 0, but we had some charge distribution placed over there, then the perpendicular component of the displacement field would not be continuous, but the jump will be proportional to the surface charge density, free surface charge density. Because all the charge distribution created by the polarization is already included in the displacement field. So these two are the conditions that we have to impose. Now, the first condition for the parallel component of the electric field basically amounts to phi is continuous. Now, the continuity of phi, okay. Now, the continuity of phi basically will tell us, okay, instead of the small r, put capital R and equate the two, and you are done. Now, the perpendicular component of the displacement field is nothing but the derivative of phi with respect to r. So this will tell me that so phi 1 at r is equal to phi capital R. Phi 2 at capital R, this is one condition that phi should satisfy. Furthermore, the second equation tells me that epsilon 1 times del phi 1 over del R, because the radial component is the perpendicular component to the surface, that's why I'm only considering the radial part. This should be equal to epsilon 2 del phi 2 by del r. Of course, both are evaluated at small r is equal to capital R. This is the other condition. So we have basically these two sets of unknowns. We don't know what C is, we don't know what B's are. To solve for them, we need two sets of equalities, relations. And this is one set of equalities, this is the other set of equalities. Basically, it will turn out that BL and CL, they are all 0 if L is different than 1. Anyway, we will continue this discussion on Wednesday. Now, any last minute questions?